Welcome everyone to the Algebraic Calculus. I'm Norman Walberger. So this is the Algebraic Calculus 2, our second course, where we're going to be slowly moving towards differential calculus. And a good starting point is to extend our arithmetic. Okay, so we've been doing arithmetic since primary school. It's time to step up a grade, and that's going to open a lot of doors for us in our understanding of calculus. So just to remind you, we started primary school with arithmetic with numbers, addition, multiplication, some rational numbers, etc. And then somewhere in high school, we learned about polynomial arithmetic, what we prefer to call polynumbers. So the way we like to think about things is a polynumber is a vertical list of numbers. They could be integers like most of my examples, but actually they could also be rational numbers, which are sort of the default number system that we adopt. So here's a polynumber 2, 1, and here's another one, minus 1, 3, and the way we add them is component-wise. And if we want to multiply them, it's a little bit more sophisticated, something called a Cauchy product. So 1, 2 times 3 minus 1. How do we get 3, 5 minus 2? Well, the top entry, which is sort of the level 0, is the product of the two level 0 fellows. 1 times 3 is 3. The level 1 guy down here, the 5, is obtained from taking the level 0 times the level 1 here and adding the level 1 here times the level 0 here. So 1 times minus 1 plus 2 times 3, that's a total of 5. And there's also an additional one at level 2, which is obtained from the product of the two level 1 terms, 2 times minus 1. Now it becomes convenient to connect this with polynomial arithmetic. We can do that by introducing the special polynumber alpha, which is 0, 1. And that way we can quickly rewrite a polynumber like this as 2 plus alpha. This one is minus 1 plus 3 alpha. And then the addition is just the usual addition of polynomials in alpha. But now, crucially, the alpha is not some variable for which it's hard for us to pin down. It's rather this very specific polynumber. Okay, and then the multiplication, like over here, 1 plus 2 alpha times 3 minus alpha, that's 3 plus 5 alpha minus 2 alpha squared. That then corresponds to the usual polynomial arithmetic. Okay, so that's great. That has been a very important framework for the Algebraic Calculus 1 course, because a lot of the basic elementary stuff with calculus really rests on polynomial arithmetic. But now, entering the Algebraic Calculus 2 course, we want to go up a level. And this is a very big jump, sort of taking a step from the high school arithmetic to college level arithmetic. So this next step up is in traditional calculus courses called power series. But we are going to call them Polyseries, because we want to separate what we're doing from the usual story, because we're approaching things in a much more finite, specifiable fashion. We're not allowed to say, let's add up the following infinite number of things. So we have to have everything on the page. And that means that it's a big challenge for us actually to bring this into a proper focus. So today's lecture is not meant to actually do that, but just to introduce these objects and kind of convince you that they are actually quite interesting and important, and that they really do enlarge our arithmetic. So what are these things? Well, from our point of view, a polyseries is like a polynumber. It's a vertical list of numbers, but with the crucial difference that it doesn't necessarily end. Okay? There's these three dots that in some sense represent an ongoing aspect of this polynumber. So it's a polynumber that's ongoing, if you like. But to say precisely what that means will require a fair amount of work for us. So it's not at all clear at this stage. But anyway, we can sort of visually understand. Here is a polyseries that starts 0, 1, 2, 3, and then carries on in some fashion. And here's another one, 1, 2, 4, 8, carries on in some fashion. Now, you might look at this one and say, well, this is looking like the polynumber with the consecutive integers down the column. And maybe that's the case, but maybe that's just a good guess and not quite correct, because we are not saying what exactly the pattern is represented by these three dots at this point. Likewise here you might say, okay, that looks like powers of 2. Well, that could be, but there are other sequences, interesting sequences that start this way and then don't carry on like you might think. Okay, so adding these things is just like with polynumbers, we add them component-wise. So in this case, we get 1, 3, 6, and 11. And then what happens afterwards, well, we don't really know, but we represent that with 3 dots. If we knew a few more terms here, then we could augment this sum also. So here then is corresponding multiplication. We choose some different ones. Here's the polynumber or polyseries, 1, 1, 1, 1, 1, and then carries on. And this one 0, 1, 3, 7, 5, and there's more. And to multiply them, we still do that Cauchy product kind of business. So 1 times 0 is 0. 1 times 1 plus 1 times 0, that's 1. I'm going to go through it this time so to make sure we all know, okay? This 4 is obtained by 1 times 3 plus 1 times 1 plus 1 times 0. So that's 3 plus 1, that's 4. This 11 is obtained by 1 times 7 plus 1 times 3 plus 1 times 1 plus 1 times 0. It's 11. This 26 is obtained by 1 times 15 plus 1 times 7 plus 1 times 3 plus 1 times 1 plus 1 times 0. You can see that what we're doing here is kind of adding up successive elements in this one, right? This is performing like a summation, really, on this sequence. So we get to 26. And if we knew more, well, then we could get more. But at this stage, we're not able to say what the next one is because we don't know what the next ones are in the 2 sequences or 2 polyseries there. Now, just as with polynumbers, we can alternatively represent what's going on with alpha notation. So here, this would be alpha plus 2 alpha squared plus 3 alpha cubed plus something going on. This is 1 plus 2 alpha plus 4 alpha squared plus 8 alpha cubed plus something further that's going on, but we don't know what. And the sum is, well, 1 plus 3 alpha plus 6 alpha squared plus 11 alpha cubed. And that we can obtain just from the information given. The higher powers of alpha, which are sort of implicit there but not known, are not going to affect these ones. So whatever these things are beyond here, it's not going to affect this computation that we have made. At the beginning, the first 4 terms are going to be 1 plus 3 alpha plus 6 alpha squared plus 11 alpha cubed. Similarly, over here, this one is 1 plus alpha squared plus alpha cubed plus alpha to the 4th, and then it keeps going. And this one is alpha, there's no constant term, plus 3 alpha squared plus 7 alpha cubed plus 15 alpha to the 4th, and it keeps going again in some fashion that we don't know. And if you just did polynomial arithmetic on this, well, you could calculate everything up to the 4th powers of alpha. You wouldn't be able to say anything about alpha to the 5th or higher because there's some unknown alpha to the 5th terms in both of these initial expressions that we don't know. So we're not able to calculate any higher coefficients, but we can determine that the initial ones are alpha plus 4 alpha squared plus 11 alpha cubed plus 26 alpha to the 4. And at this level of the polyseries written out like this horizontally in terms of alpha, how, for example, could we get this alpha cubed with an 11 in front of it? Well, we ask, how can we get alpha cubed out of this product? We can get it with 1 times alpha cubed, there's 7 of them. Or alpha times 3 alpha squared, there's 3 of them. Or alpha squared times alpha, there's 1 of them. And that's all the possibilities for a total of 7 plus 3 plus 1, which is 11. Okay? So this Cauchy product at the level of sequences or lists is exactly what we are familiar with high school polynomial algebra. But crucially, now we're recognizing that we're only stating things up to a certain point, and then beyond it, there's some indeterminacy. We don't know what's happening after that at this point. Now, it turns out, just this example here is a little bit interesting. So this is obviously kind of an obvious pattern, okay, the obvious pattern. And this here is also kind of an obvious pattern. You could get a good guess for what that is, just 1 less than powers of 2. And then it turns out that these numbers here are not without interest, 1, 4, 11, 26. They are the first of the Eulerian numbers. In Sloan's online encyclopedia of integer sequences, which is going to be playing a very interesting role in this course, that sequence is numbered A000295. Okay, Okay, that's that sequence that starts 1, 4, 11, 26. Maybe there's some zeros in front. So it turns out that these Eulerian numbers, wherever they're coming from, probably some kind of combinatorics or algebra, can be sort of generated by multiplying these two simpler polyseries. So that's kind of interesting, and we can hope that more interesting things like that will happen. All right, so it looks like there's a cute or interesting arithmetic that can be developed with these polyseries, which kind of are like polynumbers, but they carry on. But what are the connections with calculus? So it turns out that there's very good reasons for adopting this arithmetic into the algebraic calculus. So one of them comes from the integral calculus point of view that we've already been talking about at length in the Algebraic Calculus 1 course, where we were concerned with curves and signed areas determined by segments of curves. For example, from gamma of t to gamma of u, the segment of the curve determines a certain signed area, suitably interpreted with orientations, perhaps this way and then the opposite way for this little loop here. So if our curve is a very pleasant curve, for us that means it's a de Castelnau-Bézier curve. Okay, those are the most pleasant kinds of curves in calculus for sure. They are the ones for which these signed areas can be defined and calculated completely, correctly, unambiguously, precisely. Okay, so we have a very beautiful theory of signed areas for these kind of polynomially parameterized curves, or DCB curves. But a lot of curves that come up in practice are not of that pleasant kind. So we are looking for ways of extending what we already have developed in this context to a wider arena, to be able to deal with other curves. For example, even something like a circle or a hyperbola, or maybe some kind of cubic curve. So these generally are not de Castelnau-Bézier curves, and so we'd like to access integration for them in some way, and one approach to doing that is to augment our arithmetic first by including these polyseries. That's going to be a very important technology for pushing the integral calculus further. In fact, it's very much along the line of Newton's approach to the calculus, and actually what a lot of modern physicists do as well. Now, the differential calculus, which is going to be playing a bigger role in the Algebraic Calculus 2 course, concerns itself, let's say, at least initially, with the local structure of curves. So here's a lemniscate of Bernoulli. Here's its equation as an algebraic curve, sort of like a figure 8 or infinity sign. So this kind of infinity is allowed for us, okay? And suppose we have a point on this curve. Suppose we actually can find such a point. Then we might be interested in what does this curve look like near this point? The simplest answer to that question is to consider the tangent line to the curve. Okay, so that's a good approximation to the curve, but it's not really great because it's a straight line. A better approximation is to take a quadratic approximation. So one can do this. So maybe there's a parabola that approximates the curve well at that point. And maybe in fact there are higher order curves that provide better and better approximations to the curve near the point where we're interested in. So that's a primary kind of motivation in the differential calculus, is to be able to provide finer and finer descriptions or understandings of curves near some particular point or region. So a natural question might be sort of, how do we approximate a curve, say, near point P? Well, another way of approaching this, or actually kind of related, is to try to express the curve in a parametric form. Now, it turns out that this kind of curve is not a de Castelnau-Bézier curve. Okay, so you cannot parameterize it with polynumbers. That's just a fact of life. If you could, then all integral questions become a lot simpler automatically, but you can't. But what you can do, it turns out, often at least, is to sort of capture this with not polynumbers, but polyseries. So we can aspire to describing the curve gamma, at least say near the point P, by a series like this, where we have, instead of a polynumber P and another polynumber Q, we have a polyseries. A0 plus A1 alpha plus A2 alpha squared plus, and then there's more stuff. And here's another one, B0 plus B1 alpha plus B2 alpha squared plus more stuff. At this stage, we're not saying what the more stuff is, but when we allow ourselves this possibility of using this augmented arithmetic, then the possibility emerges that we can describe curves like this, which cannot be described in a DCB fashion, but with this sort of larger framework. That's great because a lot of the kinds of things that we do with DCB curves, based on essentially understanding polynumbers, can be applied to this setting because these things are almost polynumbers. Okay, so this is a really good idea, and that's going to be powerful for us, but we do need to make the step up when we're considering general curves from polynumbers to polyseries. So I hope I've provided some kind of motivation for us why we might be interested in polyseries in the context of calculus. But in fact, we can also see polyseries arising naturally in much more elementary arithmetic. So if you just start thinking about arithmetic with polynomials or polynumbers, then it doesn't take too much before you start realizing that in certain situations, it'd be really useful to be able to extend our polynumbers to have more and more terms. Sort of an ongoing kind of polynumbers, namely polyseries. So let me give you an example or two of those. So the first one comes from division. Okay? We have our four operations: addition, subtraction, multiplication. Those three are very simple, or relatively simple, with just polynumbers, and don't take us outside of polynumbers. But division, which is always the hardest arithmetical operation, that gives us problems. Just as it does for arithmetic with ordinary numbers. What's 3 divided by 5? Well, what's 17 divided by 59? These are more subtle questions, okay? And the similar kind of thing is happening here. So let me remind you of a computation that we did actually in one of the end videos of the Algebraic Calculus 1 course. We were talking about divisibility of polynumbers, how to divide one polynumber by another. I was showing you how I prefer you to do long division. And here was an example. We were dividing 1 minus alpha to the 6th by 1 minus alpha plus alpha squared. And I want to just quickly review that because doing this long division is very important. Okay? It's a very important skill that we're going to need in our development of differential calculus and working with polyseries. So what do? We ask ourselves, how many times does this polynomial sort of divide this one? And note that we've arranged our polynumbers so that they are in increasing order as we read from left to right. So the constant term first, and then the linear term, and the quadratic term as we move to the right, okay? So when we answer this question, what we do is we say, okay, let's look at the constant term. We're sort of reading from left to right. The constant term 1, okay? Here there's a constant term 1. How many of these fit into this? Well, one of them. So we take 1, we write down that 1, and we multiply this by 1, and we get that there. So we think that one of these will fit inside here because this 1 is sort of dividing that 1 there, or less than that 1. So we then subtract. We take this thing minus this. So that gives us a total of alpha minus alpha squared minus alpha to the 6th. So this one here is the result of taking this minus this. So that's like the remainder after we've removed one of these from what we started with. Okay, now we ask again, how many of these will fit into this thing here? And it's quite simple because we just look at this constant term here. That's the only thing that we're really using. We say, okay, there's an alpha here, there's a 1 here. We can take alpha of these. Okay, so we multiply this by alpha, we get alpha minus alpha squared plus alpha cubed. And then we're going to subtract this one minus this one. The alphas cancel, the alpha squareds cancel, and we get this minus this, minus alpha cubed minus alpha to the 6. Now, how many of these fit into there? We just look at the first or the lowest term, minus alpha cubed. We say minus alpha cubed of them will fit in. So we multiply this by minus alpha cubed. There it is there. We do the subtraction. We get this one here. Then how many of these fit into there? We get minus alpha to the 4 of them. And by the time we've done that, then we finally get a remainder of 0. That means that the division has been successful. We have divided this by this and obtained this. Okay, so here's the result of that. So writing it sort of in terms of a quotient, 1 minus alpha to the 6 over 1 minus alpha plus alpha squared, that equals 1 plus alpha minus alpha cubed minus alpha to the 4. And we could check that by doing a multiplication. So we could multiply both sides by this denominator here, bring that to this side here. And if we multiply this polynumber by this polynumber, expanded it all out, collected terms, simplified, we would get exactly 1 minus alpha to the 6 with nothing left over. But just as for numbers, not all divisions work so well. We can divide 24 by 6, we get an exact number 4. If we try to divide 24 by 7, well, then it's a very different story. Okay, so that also happens in the polynumber situation. For example, suppose we just change that a little bit. Now we have 1 minus alpha to the 5 divided by the same thing, 1 minus alpha plus alpha squared. So I'm going to divide using the same strategy, but now I'm going to sort of write the answers, the quotients vertically because, well, actually we'll see that they keep on going, okay? So let's start. How many of these fit into here? Well, again, we just look at the leftmost terms here and here. One of them. So here's one of them. Now we subtract this minus this. We get alpha minus alpha squared minus alpha to the 5th. How many of these fit into here? Alpha of them. So I'll put the alpha on the same line. Alpha of them. So alpha times this is alpha minus alpha squared plus alpha cubed. This minus this is, those things cancel. We still get minus alpha cubed minus alpha to the 5th. How many of these fit into this? Minus alpha cubed of them. Here we have minus alpha cubed plus alpha to the 4th minus alpha to the 5th. We do the subtraction. We get minus alpha to the 4. Actually, so far it's looking very much like what we did in the last example. And how many of these fit into minus alpha to the 4? Well, minus alpha to the 4 of them. This multiplied by minus alpha to the 4 is minus alpha to the 4 plus alpha to the 5th minus alpha to the 6. We subtract this minus this. We get minus alpha to the 5th plus alpha to the 6th. Last time we got 0. This time we're not getting 0. Okay. So we could carry on. Okay, how many of these fit into here? Well, minus alpha to the 5th. We can see that. But further ones, well, would require further work. Now, is this going to end? Like maybe if we go down 28 steps, will it finally end? No, it won't, because so far what we've got is we've got 1 minus alpha to the 5th over 1 minus alpha plus alpha squared equals 1 plus alpha minus alpha cubed minus alpha 4th minus alpha 5th. And then there's some more stuff which we haven't computed yet. And this is not going to end at alpha to the 28, because if it did, then we would have an identity that involves 1 minus alpha to the 5th equals the product of this term times this big polynumber. Okay, if this is degree 2 and this thing is of degree 28, when we multiply them, we're going to get something of degree 30, not of degree 5 like we need. So that argument shows that this procedure in this case is not going to end. It's a completely different story from the previous division that we did. It's an algorithm which will not end. And this is such an important aspect of this story, right? Now what we have here is an algorithm, a well-defined procedure that's very clearly laid out. And we're pressing the run button, and it's churning over and over and over, giving us output. Excellent, more and more and more output. But we can see that this program is not going to stop. It's not going to terminate. We do not get to the end. This just keeps on churning out more and more terms in this Polyseries. Now, my pure mathematician friends look at something like this and say, okay, well, why don't we just go to infinity? You know, get our computer and we look at the back somewhere, and there's a go to infinity button, big red button. Does your computer have such a thing? Big red button, go to infinity. And suddenly you've gone to infinity in the minds of my friends. So it's a thought experiment, which unfortunately is somehow removed from actual computational reality, because if you do this for a few hours, you will see that you're not going to be able to go to infinity. You're not going to be able to continue this thing to the end of time. So in any case, we're getting something that we could informally call a polyseries. We've divided this polynumber by this polynumber. We have not got another polynumber. We've gotten a polyseries. So this is a very good reason why having an arithmetic including polyseries is a good idea, because it allows us to do division in the world of polynumbers. Now, another kind of interesting arithmetic that we can access with polyseries that we can't access so easily with polynumbers are square roots. So for example, suppose we want to solve p squared equals 1 plus alpha. Okay, so 1 plus alpha is a very simple polynumber, and p is some other polynumber. So we're looking for a polynumber that has the property that if you square it, you're going to get 1 plus alpha. Now, it's pretty easy to see that you're not going to be able to find such a polynumber. But it turns out that if you expand your horizon a little bit and allow polyseries, that you can find such a p, at least kind of. Okay, so let me show you how that goes. So our polynumber p, we're going to represent it with unknown entries. Say p0, p1, p2, and it carries on. In this case, the pattern is obvious. And here we're multiplying p times p. And we would like the product to be this thing here, which is 1 plus alpha. So what we're going to do, and this is a fundamental sort of strategy for many such problems, is we're going to successively go through the various pi's and solve for them. Okay, so we start up at the top, at the 0 level. The top level is p0 times p0 should equal 1. So p0 squared equals 1. Well, we know what the solutions or possibilities for that are. So p0, therefore, is going to be equal to plus or minus 1. Let's say that p0 is 1. Okay, so suppose it's 1. So we have 1 now. And now we have this next entry. Okay, how do we get this next entry? Well, it's this is now going to be a 1. So 1 times p1 plus p1 times 1, that's 2p1, should equal 1. That's going to be our next thing. I'll put it maybe here. 2p0 equals 1. That tells us that p is going to be a half. Okay, so there's a half here. Okay, so this is 1, this is a half, this is unknown p2. What's that going to be? So let's look at the third entry, which here is actually a 0, but it's nothing there, but that means it's a 0. So that 0 is going to be the result of p0 times p2. That's p2. So let's write p2. And then plus p1 times p1. Well, p1 we've said is, it was not p0, sorry, this was p1, pardon me. p1 was 1 half. So p1 times p1 is 1 quarter, so 1 quarter. And then there's another p2 times p0, that's 1, so there'll be another p2. And that should be equal to 0. Okay, so we bring the 1 quarter to the other side, that's minus a quarter, then we divide by 2, we get minus 1/8. Get minus 1/8. And you could see that you could kind of carry on like this. And in fact, if you carry on a little bit further, we get p equals 1 plus 1/2 alpha minus 1/8 alpha squared plus 1/16 of alpha cubed, then minus 5 over 128 alpha to the 4 plus 7 over 256 alpha to the 5, and then it keeps going. Actually, the next one is negative. And just as in the division case, it doesn't stop. We've outlined an algorithm that allows us to sequentially calculate more and more of these PIs with the understanding that the algorithm doesn't end. We never get to the end, because if we got to the end, we had some polynomial or polynumber of degree 100, then its square is going to be a degree 200. It's not going to be equal to this thing. Okay, so there's no way we're going to get a polynumber answer out of this. This is necessarily going to have to keep on going in some sense. The algorithm does not stop. But there's going to be another solution, and that's when we take minus p instead of this p. So just multiply all of those by negatives, and that's going to have the property that when you square it, you're still going to get the same thing as you did before. Okay, this is quite interesting. This is actually a very important Polyseries, although we're just describing the first 5 or 6 terms here. Okay, it keeps on going. But there will be a lot of physicists, for example, who will know this off by heart, okay, because it's an important tool for a lot of calculations. If you want to calculate a square root in a lot of situations, it ends up being close to this. All right, so that's an important example of how a Polyseries allows us to solve a kind of equation that we have no hope of solving originally with just polynumbers. Okay, so this is such an important technology. I want to show you the same kind of problem, but with a little bit more sophisticated right-hand side. So let's try to solve q squared equals 1 plus alpha minus alpha squared. We're looking for a polynumber, or probably a Polyseries, that will satisfy this equation. And we suppose that q is given by q0, q1, q2, some coefficients or entries which are to be determined. And our job is to determine them. We're going to do so one at a time, starting from the top. So q0 times q0 equals 1. Okay, so I'm going to put the result here. So we have q0 squared equals 1. That's our top line. So let's say that q0 is 1. There's 2 possibilities as I had before. I'm just going to show you one possibility. Okay, so q0 is now 1. Okay, now what's the next line? 1 times q1 plus 1 times q1, so that's 2q1 is going to be 1. Oh, I get the same thing as we did last time. q1 is going to be 1/2. Okay, what's the next one? So we have q2, and there's another 2q2, so there's 2q2 plus this 1/2 times 1/2, so that's a quarter, equals, and now minus 1. Okay, so minus 1. Bring this to the other side, so that's minus 5 quarters divided by 2. That's minus 5/8. So we could carry on, right? We could carry on, but what we're going to get is something like this. P equals 1 plus 1/2 alpha minus 5/8 alpha squared, and then plus 5/16 alpha cubed minus 45 over 128 alpha to the 4 plus 95 over 256 alpha to the 5th, and then, well, we could keep going. Again, we have a pretty clear algorithm. You could program a computer to do this, but there's lots of software that will do it very quickly anyway. But you could program a computer to do this quite pleasantly, and then you could churn out a few thousand or a million entries in this Polyseries. And this is how it would start. There's another one where we just multiply this one by minus 1. I guess we're not talking about P, we're talking about Q, aren't we? Okay, pardon me, Q. So let's put a box around there. That's our solution to this quadratic equation in polynumbers, but the solution is this Polyseries. And as you can kind of guess, it's maybe not entirely easy to predict what the general coefficient is that's going to be in front of alpha to the n, although it's maybe not impossible either. So in the course proper, you'll have a chance to practice a lot of different examples to strengthen this technology. But here's another sort of step up where we look at cube roots instead of square roots. Suppose we're trying to solve this equation, r cubed equals 1 plus alpha. Well, let's let r be the polyseries, starting with r0 and then r1, r2, r3, and so on. And we have to cube this thing and set it equal to this polynumber 1 plus alpha. So it turns out that when you cube this, you get a polyseries whose terms successively get bigger and bigger, but they are polynomials in the entries up to this point. So let's say we're going up to this point here, this number 3 entry, this is sort of degree 0, 1, 2, 3. So this degree 3 entry is a polynomial combination of all the previous ones. But it has a crucial additional property. So let's have a look at successive ones. So the top one is r0 cubed. We're setting that equal to 1, so one solution is to let that be 1. So suppose r0 is equal to 1. Then the next one would be 3 times r1 equals this one here. So 3 times r1, that means that r1 has to be 1/3. So there's the 1/3. The next line, so we're saying r0 is 1 and r1 is 1/3. So this would be 3 times 1/3 squared, so it's like a total of 1/3. And this is just 3r2. And that's supposed to equal the second entry here, which is a 0. Okay, so what's that give us? So I guess we get minus 3 divided by 3, so that's minus 1/9. That was why we get a minus 1/9 there for the alpha squared term. And then you could check that the next one here, the r3 term, crucially, is appearing only linearly here. It's appearing linearly here, linearly here. So that's very pleasant because it means that we can recursively solve for these various r's. Okay, once we have, at this stage, r0, r1, r2, then this is a linear equation, set it equal to 0, for r3. Linear equations we can always solve, especially since the coefficient is non-zero, right? We're saying r0 is 1. So this coefficient here is not 0. That means we can solve for r3. And we would get 5/81. And we can carry on this way. We get this polyseries. So this is kind of a strange new arithmetic, isn't it? Right? We're solving an equation like this in polynumbers or polynomials, and we're getting answers which are polynomials which carry on, which we're calling polyseries. And it's not clear what this means. Like, how are we supposed to interpret this? What is actually the definition of this r? Right now it's in quotes because there's this crucial 3 dots there, and we haven't said what that really means. Are we obliged to spell out what the actual coefficients are? Or is it enough to specify the algorithm? Or can we just write something down like this and then add 3 dots and say, well, this is the object? These are very subtle questions that we have to deal with. So that's definitely a question about all this. What is really happening? And then another obviously interesting question is there a formula for these coefficients? You know, there's some kind of pattern here, it seems, but a little bit of a pattern, some powers of 3 involved here. Can we write down a formula for the coefficients? Well, Isaac Newton, back in the 17th century, worked this out in one of the really great discoveries of modern mathematics. He realized what's going on with this equation and with the square root equation, and in fact with a much more general class of equations. And this is really his generalized binomial series. Okay, so that's great. We're going to touch base with Newton's work, and that's going to give us new insight into the structure of these polyseries that are coming up with questions like this. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.